Yeah, awesome. I guess it's working. So, yeah. So I'm Spiros Casabis. I'm a fourth year PhD student at the University of Michigan. Um, this is part of the research that the Solstice team does, the Solar Storage Terrestrial Impact Center. We do a lot of things when it comes to like heliophysics. We are pretty new at like using machine learning in heliophysics, but this is something that we're trying to get more into. This is actually one of the first papers Solstice has published in uh, in the machine learning and heliophysics. Uh, so the paper is up on AGU right now, like it got published like 2 weeks ago. So you know, go take a look at that. But yeah, so what we're trying to do is to create a machine learning capability. We said we'll forecast solar energetic particle events with improved accuracy and reliability. Here I have a summary of what we use. Um, the big thing about this paper and what we're discussing and trying to do is the SMART data. So Monica Boba from Stanford's the Hansen Heliophysics Laboratory, she provided us with this new piece of data. It should be public now, but back in the day, it wasn't public, but I think it went public like half a year ago or so. So yeah, we are trying to use this new data product called Space Weather Michelson Doppler Imager data, the active region patches of that to predict SEP events. So SMARTs are derived from maps of the solar surface of the magnetic field taken by, of course, MDI, which is on board of the SOHO satellite. SOHO was deployed in 1996 and it went up to like 2010. So this is the time frame we're using data from. So like about 14 years of data. And essentially what we do is we are trying to label those active regions or those smart active regions that produced SCPs as positive and the rest that did not as negative, regardless of whether they produced a flare or not. So these data we use to train different types of machine learning methods, support vector machines, and some regression models. So these are the machine learning models that we're using. We use the SVMs like with 4 different filters. And then we also use like 2 linear models, ridge regression and then logistic regression to just test the smart data. Now, the smart data and the smart data is the most important part of this. So essentially, this paper is an evaluation of like how smart data can be used for like SEP prediction. It's not, we don't focus that much on like beating other SEP prediction models. We mostly focus on like whether like this new piece of data, like smart data, can be used like SEP prediction alone or like to augment other existing data sets. So from the magnetograms that are measured by SOHO, we extract 5 different values. The first 3 are extracted straight away. Monica has done this work, and so we get the data as is. So it's the total unsigned flux, the vertical field gradient, and the R value. And then we also infer 2 more predictors, which is the active region angular distance and the active region area. So we essentially take the coordinates and we convert it into like these 2 predictions. So these are the 5 predictors that we're gonna feed into like our machine learning method in order to do the prediction. These are the key values, and now what we have here as flare data is, and I'm going to explain what what these graphs show. But because this is quite unique, SEP prediction is like a pretty new thing. There's not many models that we could compare with, especially using like this new data product. So what we did in order to compare our data was using the flare data itself. So it's a two-step process essentially. We use from every smart active region, we know the flares that occurred within this active region. And if we know that a flare led to an SCP, then this flare we consider as positive. The rest of them we consider as negative. And we use the flare data, the flare angular distance from where the flare occurred, and the flare peak intensity. We also feed these into the different machine learning model in order to see how using the flare data would predict SCPs. Now, this is kind of like, I wouldn't say cheating using the flare data, because it means that you know that a flare occurred and you have like a very small leading time to the SCP in order to predict the SCP, which is not what we desire. We desire to predict an SCP even without knowing whether a flare occurred or not before. Now, what these histograms show is in green is positive, in red is negative, and these histograms show essentially the overlap between the positive and the negative flares. The positive flares are the ones that produce an SCP, and the negative are the ones that fail. For example, you can see that here for the total unsent flags, when we have like a smart predictor that has like quite a big total unsent flags, it is much more probable that it is going to lead to an SCP, whereas the ones that do not have that big of a total unsent flags tend to be negative. Now, there is a lot of overlap between the rest of the smart values, which kind of gives us an idea that this is a very tough task. But yes, and obviously we can see that only using the smart data without any flare knowledge is a much more difficult task, because you can see that if we use the flare intensity, there is a very small overlap, which means that knowing the flare intensity, knowing the intensity of the flare really happens, can tell you very well whether it's going to lead to an SCP or not. But yet again, using this data means that you have like a very small time window of SCP prediction. And this is what we show here. We show the time difference, the time window between when the SCP happens and when the positive and the negative flares occur. They're pretty much the same, but the thing is that when using only the smart data, we get this extra leading time. I should also note that the smart data compared to like other data sets, like the ones that the HMI provide us, is much lower in that resolution. So the SOHO satellite takes images of the sun every 96 minutes, whereas HMI takes pictures of the sun every 12 minutes. So these 96 minutes gives us like a pretty big time window for prediction. Now, when feeding only the smart data on the machine learning model, this is the best we could get, and this is for polynomial SVM. We get a prediction of like around 70% accuracy, and this is when we use balanced basis. So obviously and this is a problem within the community, and especially when we do SEP predictions. We think like these 14 years that Soho was getting data, it was only around 40 SEP events within these 14 years. So our positive data set is comprised of like only 40 timeframes of smart data, and then the negative is like more than 2,000 or 3,000. So there is like it's like a very unbalanced data set. Now, when we do like a random bag sampling on like an SVM model, we can see that even the smart data can kind of infer whether there is going to be an SEP or not. It's like a pretty high accuracy, like 3 out of 4 times. And this is when we also use flare data. When you use the flare data, you can get up to like 90%, because as I said, the flare peak intensity is a very good predictor of saying whether there is going to be a SEP or not. Now, we also do an analysis for like quiet active regions. So like obviously on the smart data set, there's active regions that do not lead to a flare. So one of the questions we had from our referees for the paper is what happens when we have an active region that is not producing a flare, because we based our entire analysis to only the flares that produced an SEP. And what we prove here is that quiet active regions, when it comes to like the smart data that they show, so very low overlap between like positive and quiet. So for a machine learning model, predicting whether there was an SEP versus whether an active region was quiet is like a trivial and a very easy question to solve. So we treat the quiet active regions as noise. We don't so yeah, this is like a summary. So our models, when it comes to like an experimental setup, as I said, like a random picking from like, for example, when we have like, when we train like the 40 positives that we have, and then 40 random negatives, can score pretty high at around like 70–75%, like a variety of like different machine learning models. And if you use the flare knowledge too, you can up this to like 90%. Now, adding to this on the paper, we have also done some tests more for operational use. So what we do is we train all these models on like the full data set. So we train on this vastly imbalanced like 3,000 flares, positive and negative flares, and then 40 negative flares, positive flares. And the accuracy drops significantly down to like about 50–55%. Which is not good, which means that the smart data set, and this is pretty much like the outcome of this research. We show that the smart data set can infer or can give some information on like whether an SEP, whether a flare is going to lead to an SEP, but it alone would not be like a very good data set to predict. So what we propose is for the smart data set to be used as a piece of data to augment other data sets. So yeah, that's what we've done. I rushed through it, so if you have any questions.
I have a question, a simple one.
Yeah, of course.
What is the why